The third part means I want to start with again as I finished. So we had ideal gas mixture. We start with ideal gas mixture, and we see that Pk, that is the partial pressure of component K, right? Partial pressure of component K equals to xk times P, where xk is the mole fraction of component K. Now P is summation of Pk, right? K equal to 1 to C if you have C components, which is summation xkp, and as you can see that P summation xk, P is the total pressure which is constant. So you see P equal to P, so it's a consistent definition, right? In the partial. So this is a consistent definition, right? Partial pressure equal to mole fraction is total pressure. Now, as you know, dg equals to minus st plus vdp. Again, this relation works for extensive property, works for also the partial molar property, as we have already told. So dgk bar is equal to d mu k. Dgk bar is what? The gk bar is the partial molar free energy. So d of gk bar. So d of gk bar means differential of gk bar. Okay, the change or d mu k, the d of mu k, that is the differential of the chemical potential of component K. So chemical potential is nothing but the partial molar free energy of component K in the mixture, which is equals to minus Sk bar. Minus Sk bar is the partial molar entropy of component K times dt plus Vk bar, which is the partial molar volume of component K times dP. Now we are basically telling the temperature is fixed. Let us assume that the mixing process is isothermal, right? Let's assume the mixing process is isothermal. Okay, we are telling mixing process occurs at a given temperature. Okay, and the total pressure is P, but we are basically telling the total pressure is P, and but P is not constant, but the temperature is constant, or temperature the mixing process is isothermal. So as a result, dt will go to dt equal to 0. dt equal to 0. So this is becoming equal to, so minus sk bar dt. So this one goes to 0. So you still have Vk bar dp. So dgk bar equals to Vk bar dp. Now V, the total volume V equals to nRT by P, because it's an ideal gas, right? It's an ideal gas. So which is RT by P summation K equal to 1 to C Nk. Now V equals to RT by P N, and that is summation Nk, and Vk bar equals to del V del Nk, which is nothing but del V del Nk, keeping Tp Nj not equal to K. And now if you look at that, so it is basically Vk bar is V is what? RT by P times N. So del Nk. So basically this is basically del Nk, right? Where now here what does this mean? It means that only K is in K component, the mole number of K component K is varying, and in J for all other components the mole number is fixed. Okay, so and T, so basically T is fixed, say P is fixed, say, then this becomes equals to nothing but del Nk is nothing but 1. So this becomes nothing but RT by P, right? So Vk bar is RT by P. Now since d mu k equals to Vk bar dp, you can write d mu k if I integrate. So if I integrate d mu k, and I tell that this is a pure component. So if I tell that this is mu k, that is a solution, and this is the mu k 0, that is component k in the pure form, then mu k minus mu k 0 is equals to P to Pk. See, P is the total pressure, right? And that was when it was mu k 0, right? That was the pressure. That right, when it is not mixed, then the pressure was P. When it became mixed, then it became partial pressure Pk, right? Component K only exerts partial pressure, because component K has a mole fraction, and mole fraction times partial pressure again becomes total pressure. So this is equals to Vk bar dp. So this becomes RTln. So if you do this, what is Vk bar? Vk bar is RT by P dp. So RT by P, so integral RT by P dp, you can take RT out, and then becomes dP by P, which is basically RT integral dP by P. So this becomes RT ln P, because T is fixed isothermal. So if I look at that, so this is RT ln P plus some integration constant, right? Some integration constant K1, okay, or Ki. Now this RT ln P, but you don't require this integration constant if you have the limits, right? So P, when mu K0 was there, that is in the pure state, you had the pressure P, right? That was the correspondence. When it is mu K, now in the mixture, your pressure is Pk, right? So Pk is the partial pressure of component K. So this becomes RT ln Pk by P, right? So mu K minus mu K0 becomes RT ln Pk by P. Now Pk is xkp. So delta mu K, which is mu K minus mu K0, or which is equal to delta Gk bar, which is relative partial molar free energy, or this is relative change in chemical potential, you can call it, due to mixing. Of component K due to mixing. Which is mu K minus mu K naught, which is equals to delta Gk bar, is nothing but RT ln xk, because Pk by this implies Pk by P equal to xk, mole fraction of component K. So delta mu K, which is delta Gk bar, is RT ln xk. Now you see del delta mu K del T at P and K is nothing but del delta Gk bar del T, right? That's this one, right? So same thing, which is now it is like del RT ln xk del T. So basically, if that is so, this becomes R ln xk, right? This becomes, because Nk is fixed, right? So this becomes R ln xk. See, so from delta mu K, I got the derivative with respect to temperature, which is nothing but R ln xk. Now del delta mu K del P at fixed temperature Nk now is nothing but, as you can see, there is no P term. So basically, so with respect to P, the variation in the partial molar free energy or variation in the change in chemical potential due to mixing is equal to 0, right? Because delta Gk bar is RT ln xk, or delta mu K is RT ln xk. So with respect to P, if I take a partial derivative, then with respect to P there is no term, so this becomes equal to 0. So you have these two terms, and what you know, delta Sk bar, if you look at this equation, dg equals to vdp, so basically del G del Tp equal to minus S, right? Del G del Tp equal to minus S. So basically you can write the same thing, so or S equals to minus del G del Tp. So this means that this relation also follows, delta Sk bar equals to minus of the negative of the partial derivative of the relative partial molar Gibbs free energy, right? The negative of the partial derivative of relative partial molar Gibbs free energy with respect to temperature, right? So this relation follows, right? Because S equals to minus del G del T, right? So this is what exactly we are writing here. So this is P and we are writing Nk. Now if that is so, then this becomes minus of, so this delta Gk bar and delta mu K is the same. So this becomes equals to minus, because this we know as, since we know that this guy equal to R ln xk. So now here this is only a negative sign that is missing. So this is a negative sign, and the same thing, that is this, comes in. So this becomes minus R ln xk. Actually, this becomes minus R ln xk. Okay. So if you see this is actually quite interesting, because see, xk is mole fraction. So xk has to be, so if you see that, what did we get? We got delta mu k, which is RT ln xk, and then delta mu k del t at constant pressure and nk equals to R ln xk, then delta sk bar equals to minus of delta mu k del t, right, from the definition, right, because delta mu k is nothing but minus delta gk bar, right, del t at constant pressure and nk, which is equals to minus, right, because delta mu k del t is R ln xk, so this is minus of R ln xk. Now see, xk, the maximum value can be 1. Now if it is 1, then R ln 1 becomes delta sk becomes 0. Sk bar becomes 0, right? But xk is not really 1 if you have multi-component. So if you have multi-components, sk is always less than 1. So ln xk, when xk is less than 1, okay, xk is between 0 and 1. So basically xk is between 0 and 1. Then ln xk is negative. R, and there is a minus sign here. So R is positive. R is positive. Ln xk is negative. R is positive, and then there is a minus sign. So this has to be greater than 0, right? So this has to be greater than 0. So this is what you can always check, okay? What you are deriving, does it make sense? Yes, the entropy of mixing, the partial molar, the change in partial molar entropy due to mixing, the change in partial molar entropy of component K due to mixing has to be greater than 0, right? Has to be greater than 0. And this is what we are proving, because we are getting minus R ln xk, right, for this ideal gas mixture. So that's fine. Now if you see delta Vk bar, which is nothing but del P, right? Del G del P is V, right? So delta mu K del P at T and K. So that's what I have written here, which is delta same as, because delta mu K and these are the same at T and K, and we have already seen that this is equal to 0. So if you see that for ideal gas mixture, the change in partial molar volume of component K due to mixing is 0, right? Now we also know delta Gk bar or delta mu K is delta Hk bar, which is the partial molar enthalpy. Delta Hk bar is partial molar enthalpy of component K due to mixing, and the change in partial molar enthalpy of, or relative partial molar enthalpy of component K due to mixing, minus T delta Sk bar, which is again relative partial molar entropy of component K due to mixing. And now you have delta Gk bar, which is, or delta mu K, which is RT ln xk, right? This is RT ln xk, which is delta Hk bar minus T, and this is delta Sk bar is minus R ln xk, right? We have shown that. So minus and minus is becomes plus, and you have T, so this becomes plus RT ln xk, and here also RT ln xk. So delta Hk bar, which is the relative partial molar enthalpy or change in partial molar enthalpy of component K due to mixing, is equal to 0, right? So delta, you can also prove it this way, that delta Hk bar is delta mu K plus T delta Sk, which is delta mu K minus T delta mu K del T. You get the same expression 0. So delta Hk bar, that's the change in partial molar enthalpy due to mixing, is 0, right? Now as you can see here, so delta mu K also can be written as T delta mu K del T. Is this possible? Yes, because this is R ln xk, so this becomes equals to RT ln xk. Now you can use this term here, and you will get the same relation. Delta Hk bar is equal to 0. Okay, so delta sk bar equal to 0. So let us get back. I'm sorry for this disturbance that has happened. Some applications in my computer suddenly popped up and created some issue. I'm really apologizing for this. So as you can see here, what we got is delta mu k bar. So if you look at that, we started with this delta mu k or delta, which is nothing but delta g k bar, which is nothing but relative partial molar gives free energy or just free energy of component K due to mixing. Now from delta mu K, once I know delta mu K, I can know del delta mu K del T at fixed P and Nk, and then I can know delta S K bar, and that's what I got, minus R ln x K, and I proved that it has to be minus R ln x K, so as that the delta S K bar has to be greater than 0. It's the partial molar and change in partial molar entropy due to mixing of component K. And then delta V K bar we got 0, delta H K bar also we got 0, right, for the ideal gas mixture, right? So now since delta H K bar is 0, so UK, basically H equals to U plus PV, right? U plus PV. So you can write delta HK bar equals to delta UK bar plus P delta VK bar. Okay, P is the rotor pressure. So this becomes, so therefore delta UK bar equals to delta HK bar minus P delta VK bar, which is equal to 0, right? And delta FK bar, that is the relative, so this is the relative partial molar Helmholtz free energy. Helmholtz free energy of component K due to mixing, which is delta UK bar, which is 0, minus T delta SK bar, and then delta SK bar is minus R ln xk. So minus R ln xk into minus T becomes RT ln xk, which is same as delta GK bar or delta, so basically delta GK bar or delta mu K. So the advantage of this approach is this, that see, it's an ideal gas mixture, so it's like an ideal solution. So in this ideal solution or ideal mixture where there is no interaction, once you got delta mu K bar as RT ln xk, how did you get RT ln xk? From the Dalton's law of partial pressure, right? You used the integration and you got delta mu K, right, which is mu K minus mu K 0, which came out to be RT ln xk. You got all the other properties that you cannot measure directly. So you cannot measure directly delta H or delta HK bar or delta GK bar, even delta VK bar. Measuring these directly is very difficult, right? These partial molar properties, but you can estimate them once you know the change in chemical potential of component K due to mixing, right? Once I know that, okay, for this ideal mixture or for this ideal gas mixture or this ideal solution, okay, where there is no interaction between atoms, I could actually get all these indirectly measurable quantities, right? So that's the idea. So if you now look at this, it's a very interesting thing here that you get delta SK bar for this ideal mixing with delta SK bar equals to minus R ln xk. Now delta S mix is nothing but, as you know, any property Z, this is the extensive property Z, equals to NK ZK bar, okay, and summation over K equals to 1 to R, where R is the number of components, okay, small r, or 1 to C, you can call it 1 to C, where C is the number of components. Now if you see delta S mix is K equal to 1 to C Nk delta S K bar, right, which is minus R Nk ln Xk. Now Nk, summation Nk is N, right, minus R Nk ln Xk. So now this is your delta S mix, right? This is the total change in entropy, right? This is a total or extensive. This is an extensive parameter, right? Delta S mix is an extensive parameter because it is the total change in entropy, and it depends on the extent of the system, right? That is the total mole number of the system, M. Now, if I tell delta S M mix, that is the molar. This is the molar entropy. Is a molar. So let us define this as molar entropy of mixing. It's not partial molar, right? It is overall, right? But it's the molar per mole entropy of mixing per mole. We can also write that. Okay, which is delta S mix. That's the extensive property by N. N is the total number of moles, which is basically minus R. Now Nk by N is nothing but Xk. So you have minus R summation Xk ln Xk, or since K is as you know, these are repeated indices. K is operating coming twice, so repeated indices we can use any repeated index, right? You can make it K or I does not matter. So instead of K equal to 1 to R or K equal to 1 to C, let us call it C still. Just call it C, and this guy also C. Okay, so that you don't get confused anytime. So this is the number of C. C is the number of components. So basically you get minus R I equal to 1 to C Xi ln Xi. Now if you remember, when we looked at this statistical interpretation, okay, and made a connection, right, used this Boltzmann's hypothesis or Boltzmann's law. Remember statistical mechanical interpretation of entropy, and there we wrote KB ln omega. Omega is the number of configurations, and we looked at a binary solution KB ln n factorial by n factorial n b factorial. Then we looked at Starling's approximation. I don't want to go into through this in detail. I think in the lecture of week 4 or 5, I think 5, you will get all of these, right? We the statistical mechanical when we looked at the elements of statistical thermodynamics, right? And then we looked at the Starling's approximation. And then we went on doing this calculation, and then we found that we got into the same random mixing or this number of configurations for this binary law of A and B, or binary solution, right? It's a binary solution of A and B. The components gave me NKB equal to R, and we got minus R XL and XA plus XB and XB. Then I generalized it, and it becomes S equals to minus R I equal to 1 to K. Okay, minus R, so I can write here equal to 1 to C Xi ln Xi. Okay, so this, what I want to say here is that this guy that we obtain here, okay, for this for mixing from molecular interpretation, right? We are considering number of molecules, right? In Na molecules of A, Nb molecules of B, and in looking at this mole fraction of A, mole fraction of B, but we start from Boltzmann's hypothesis, we come to this, right, from the statistical mechanical version. But you can see here that we got the same expression for this ideal gas mixture or ideal mixing, where there is no interaction. If we do not consider interaction between atoms, what I get is the delta HM mix is 0, right, because delta HK bar is 0. Therefore, the sum of delta HK bar at the overall delta H peaks has to be equal to 0, because delta HK bar for any component K, the partial molar enthalpy due to mixing is 0 when you have no interactions between the atoms, right? So that is what we assume, that it's an ideal mixing. So ideal mixing means no interaction between the atoms. Each component acts as if it is occupying the entire volume, right? So that's the idea. And as for ideal mixing, so if you look at that, the entropy of mixing, the molar entropy of mixing comes out to be minus R Xi ln Xi, and from the statistical mechanical interpretation of entropy, okay, and looking at the configurational entropy, if we look at the configurational entropy of several components, right, where the number of components is C, we get back the same expression, minus R Xi ln Xi, right? So you can see that there is a very nice connect here. Okay, so you can see an exactly same connect here. So basically, ideal solution you get from whatever approach you want, whether it is the molecular approach or whether it is or statistical mechanical approach, like approach with particles using interaction. But remember, in ideal solution, no interaction between particles. That's what we assumed here. Okay, and we got back minus R xi ln xi, and we get the same expression here. So this is the delta Sm mix, like molar entropy of mixing. Now, if you look at the molar free energy of mixing, this becomes RT xi ln xi, because delta G mix is delta Hm mix minus T times delta Sm mix. So therefore there is a T and minus is there. So minus and minus, it becomes plus. So this comes because of this, because delta G, the idea is delta Gm equals delta Hm minus T delta Sm. Now, if you see that for mixing, ideal mixing, when there is no interaction between particles, this guy is 0, right? As a result, this is 0, and this is minus R xi ln xi, and then there is a T and there is a minus sign, so this becomes plus RT xi ln xi. Obviously, you can see from here that at any temperature it has to be negative, right? So ideal for an ideal solution, right? And if you look at that, delta Hm mix is 0, delta Vm mix is 0, delta Fm mix is same as delta Gm mix, which is what the this is the Helmholtz free energy of mixing. And if you look at the delta Um, which is the internal energy of mixing, again it becomes 0 because there is no interaction between the particles, between the constituents. Now delta Sm mix, as for all T, okay, it's independent of temperature because it's minus R xi, it is basically minus R xi ln xi, right? Minus R xi ln xi, and basically it has a maximum value at 0.5, okay, for a binary system, right? When x1 equals to x2, x1 equals to x2 equal to 0.5, then delta Sm makes the maximum, we get the maximum, so is maximum when x1 equals to x2 to 0.5. You can easily show that. I have shown that before, right? And if you plot it, then you can see the delta Sm mix for all temperatures, because delta Sm mix is having minus R xi ln xi, it's independent of temperature. So you can see that this has this nice curve, and you see, if you look at binary solution, the maximum value is for x1 equal to x2 equal to 0.5, and that comes out to be very near 6. If you multiply, you can easily see 8.314, 0.67, I think, and you will get very close to 6. And if you look at now delta Gm mix, it's 0, it's negative for all temperatures, right? For all, apart from T equal to 0, obviously T equal to 0 Kelvin, this will be RT xi ln xi summation over all i's, over all components. So if T equal to 0, then delta Gm mix equal to 0. Otherwise, it is negative, right? And it goes to negative, and as a function of temperature, so temperature is increasing this way, downward. Temperature increases downward. Temperature increases this way. So this is at a lower temperature. This is at a even higher temperature. Higher temperature. The higher the temperature, the more negative it is, right? But remember, delta Hm mix or delta Vm mix, these are all 0. And if it's 0, then you can just draw it using a horizon. So there is no variation over the entire composition range. There is no variation with temperature. It's all 0. So you can draw it by using a horizontal line about the y-axis value of 0, right? So delta Vm mix or delta Hm mix has the same. So if you look at delta Hm mix, it also has the same nature. This is for ideal solutions, that is solutions with no interactions between particles. Okay, so now this is for ideal gas, right? Vk bar equals to RT by P. Now in real gas, Vk bar is not equal to RT by P. It is that there is a difference which is called alpha k. There is a difference alpha k, which is Vk bar minus RT by P. Now, if you look at delta mu k and you integrate, you get Vk bar dP, which is nothing but alpha k plus, right? Because if I take this side, then this is alpha k plus RT by P dP. So this is alpha k dP from P to Pk, because P is when there is no mixing, right? There is no mixing, right? So P is for the pure component, and Pk is the partial pressure after mixing, right? In the real solution. So delta mu k comes out to mu k minus mu k naught, which is equals to, we can write RT ln Fk by P, where Fk is the fugacity. We call it fugacity of component K. Okay, so this is called fugacity of component K. Okay, so now you have P to Pk alpha k dP plus RT ln Pk by P, so which is RT ln Fk by P into P by Pk, which is basically, so if you just do a little bit of algebraic manipulation, you get this term, which is RT ln Fk by Pk equals to P to Pk alpha k dP. Now ln Fk by Pk, that means basically comes equal to, so if you have this delta mu k, you have this term, and you have RT ln Pk by P. Now you are telling that this guy is the same as this guy, and that is why you can write this term. Okay, you can do a little bit of algebraic manipulation to show. So basically RT ln Fk by P is this integral plus RT ln Pk by P. Now I am taking it on the other side, so it becomes RT ln Fk by P minus RT ln Pk by P, which is RT ln Fk by P into P by Pk, which becomes RT ln Fk by Pk, right? Which is equal to integral alpha k dP. Now if you see, ln Fk by Pk equals to 1 by RT integral alpha k dP. From P again is for the no mixing case, right? And Pk becomes the partial pressure after mixing. This is P is before mixing, right? Total pressure, right? When each component has a pressure of P, right? So because this is before mixing, and this is each component now exerts a partial pressure Pk. Okay, now Fk now becomes Pk times exponential 1 by RT P to Pk alpha k dP. Now alpha k tends to 0. When alpha k tends to 0, say for example, when real solution behaves ideally, then alpha k tends to 0. If that is so, if alpha k tends to 0, then this term tends to 0, and so overall e to the power 0 is 1, so Fk tends to Pk, right? Fk, the fugacity tends to the fugacity of component K, now it basically becomes equal to the partial pressure of component K, right? So if Fk is, as I told you, is a fugacity of component K. Now as you know from the definition of activity of component K, that delta mu K, which is mu K minus mu K 0, mu K minus mu K 0 equals to delta mu K, which is RT ln AK, which is RT ln Fk by P, right? And therefore the relation between activity and fugacity is given by AK equals to Fk by P, right? Now P is the pressure in the reference state, right, for component K, right? That's the pressure all components will have, right, will experience. So that is the pressure in the reference state, right, when there is no mixing. Now AK equals to Fk by P, right? And fugacity is generally, remember, activity is a more generalized term, right? Activity is for any type of solution we can use, but fugacity is specially for gas mixture, because we bring in pressure here in the definition, right? So as I told you, delta mu K is RT ln AK, and you know that now if I do for this generalized form, this is a generalized solution, right? We are not approximating any ideality, we are not approximating anything. So we are telling AK, we deal with AK, we tell gamma K is not equal to 1, right? In the ideal case, AK equals to xk, isn't it? So AK equals to xk, that means gamma K that is the activity coefficient, is equal to 1. Correct? That is the ideal case. This is the ideal case. Ideal solution. But in general, you have del delta mu k del t, which is r ln a k plus r t del ln a k del t, and or you can write this way, because delta mu k del t, right? This is r ln a k plus r t del ln a k del t, because I don't know how a k changes with temperature, right? So I am delta mu k del p is r t del ln a k del p at t and k. So fixed is t and k. So these terms are additional terms that you are seeing, right? This becomes equal to 0, right? This becomes equal to 0, and here it becomes r ln x, because a equals to x. So it becomes r ln x k, right? In general, so r delta mu k del t becomes r ln x k when it's an ideal solution. But now it is r ln a k plus r t times this term. So this term becomes very, very important. This term becomes important. This term also becomes important. Okay, now you have again, if you know activity of one component, you can get the activity of other component. How? Again, using the Gibbs-Duane integration that we have done previously in the 7th week. So you have x1 d delta mu 1 plus x2 d delta mu 2 equal to 0. Now delta mu 1, if I do, which is equals to minus of, right, delta mu 1 is, if I do, it is minus of, because d delta mu 1 equals to x2 by x1 minus of x2 by x1 d delta mu 2. Now d delta mu 2 dx2 if I do, so d delta mu 2 dx2 if I do, right, you get, because this is delta mu 1, so and so this becomes x2 equal to 0, right? X2 equal to 0 is the pure component, right? x2 equal to 0 means it's pure x1, right? So basically the x1 equal to 1, x2 equal to 0 means x1 equal to 1, right? To x2, x2 is where you have some contribution of component 2, right, which is, and then there is x2 by x1 d delta mu 2, so this becomes d delta mu 2 dx2, right? So this is dx2, so dx2 I am taking the limit. So basically if I take dx2 here, the limit is this, x2 equal to 0, which is the pure solvent or pure component 1, and to some value x2, okay, that is added. So if you have that, delta mu 1 is nothing but, so if I look at this, you have delta mu 1, so if you see delta mu k equals to RT ln AK, right? So delta mu 1 is, so there should be an, so if you look at that, delta mu 1, so if you look at that, you have x1 d delta mu 1 plus x2 d delta mu 2 equal to 0, and d delta mu 1 equals to, so if you look at this, d delta mu 1 is RT d ln A1, right, and d delta mu 2 equals to RT d ln A2. Now if you do this, so you have x1 RT d ln A1, x2 RT d ln A2, R equal to 0. RT cannot be 0 because t is not equal to 0. So RT you can remove. So what you get back is the same integration. So you get here ln A1 and you get x2 to x1 d ln A2 dx2. So if I know the activity of 2, I basically can get the activity of 1, right? And the again x2 goes from x2 equal to 0, that is the pure x1, means pure 1, pure component 1, to the mixture composition, which is the x2, okay? So as A2 tends to 0, say for example, as A2 tends to 0, ln A2, so ln A2 will tend to, see if A2 tends to 0, then ln A2 will tend to minus infinity, correct? Now, as you know that AK equals to gamma kxk and delta gk bar equals to RT ln gamma kxk, now you have RT ln xk, right? You already know delta gk bar equals to RT ln xk for ideal solution. So RT ln gamma k denotes the departure from ideality, right? Because RTLN XK is already for the ideal solution. Delta GK bar equals to RTLN XK. You have defined for ideal solution where there is no interaction between particles. So this RTLN gamma K is defines the departure from ideality, right? So now you can define this as two parts. One is the ideal contribution and another is the excess over ideal, right? Which is like the deviation from ideality. So this is called delta GK bar excess, which basically I call it as deviation from ideality. Okay, so basically you can write this also as the same way. So instead of delta GK bar, I am using here delta mu K. If I use delta mu K, there is a delta mu K excess, which is deviation from ideality, and then there is a delta mu K associated with the ideality, okay, or ideal solution. And delta mu K is nothing but their RTLN XK, right? This one is this, and this is RTLN gamma K, but I don't know gamma K. Now if I tell gamma K is greater than 1, now if you look at that, if gamma K is greater than 1, then this is a positive contribution, right? If it is a RTLN gamma K is positive, right? So basically we can tell the apparent concentration of component K, is greater than the actual concentration of component K, that is XK, right? Apparent concentration has to be greater than, so if gamma K is greater than 1, the apparent concentration of component K, that is say, you can think of AK, which is gamma K XK, and gamma K is greater than 1. So obviously apparent concentration of component K is greater than the actual concentration of component K, and that gives a positive deviation. So gamma K greater than 1 basically gives a positive deviation from ideality, okay, and gamma K less than 1. Now if you see delta GK bar excess, which is delta mu K excess, or delta mu K excess, is basically RTLN gamma K. Now gamma K is less than 1, so RTLN gamma K is less than 0, so that this part becomes negative. So the apparent concentration of K is less than the actual concentration of K, correct? Because, right, if you have this, so gamma K is less than 0, gamma K is less than 1. Remember, gamma K is less than 1, so RTLN gamma K, so RTLN gamma K is less than 0, or it's negative. So RTLN gamma K is negative. So it adds to the total delta G, which is delta GK bar total, which is delta GK bar excess plus delta GK bar ideal, which is RTLN XK, right? So RTLN XK, and there is a negative term, so it comes out. So basically, what does it mean? The gamma K XK, or the apparent concentration AK, is ultimately gamma K times XK, right? And now gamma K is less than 1. So AK, basically, now that you can immediately see the apparent concentration of K now is less than the actual concentration of K. So basically, you have a component K in the solution. If there is a deviation from ideality, that means there is a positive or negative gamma K. When it is a not positive or negative, you have a gamma K which can be greater than 1 or less than 1. If you have a gamma K less than 1, then ln gamma K is less than 0, right? Ln gamma K is less than 0, or RT ln gamma K is less than 0, because R is positive, right? R is positive, T is positive. So ln gamma K is less than 0 means gamma K has to be negative, has to be less than 1. Gamma K does not have to be negative. Gamma K is not negative. Gamma K is less than 1. So gamma K is less than 1. So AK equals to say 0.9 XK. So that means the apparent concentration or the activity of component K in the solution is less than the actual concentration of K, which is XK. So that gives me negative deviation from ideality. Okay, so ideality means AK equals to XK. If AK equals to 0.9 XK, then it is or gamma K can be some expression which is a function of temperature, composition, pressure, right? So we will come to that. We will come to these different real solutions. Okay, so what I am trying to say here is that depending on the value of the coefficient, because remember this RTLN gamma K is what gives you this is the excess part, RTLN gamma K. Now if gamma K is greater than 1, this is positive, so there is a positive deviation from ideality. So this is your ideality, and there is if this is positive, RTLN gamma K is greater than 0. If it is greater than 0, then this adds to this. So delta mu k for the real solution has a positive deviation from ideality. Okay, there is a positive deviation from ideality, and here it is a negative. When gamma k is less than 1, then you have a negative deviation from ideality. Okay, so now you write down this. There is this r ln gamma k. You can have this del n ln gamma k del t, right? Because now see, gamma k can be a function of temperature, gamma k can be a function of pressure, right? Gamma k can be a function of pressure. So if you look at this partial derivatives, by the way, this is if I do this, then this is not correct. This has to be p. This has to be p. Del delta mu k del p, which is RT del n gamma k del p at fixed temperature and nk. Okay, so another thing, if you have this is again Gibbs Duhem relation, right? This is Gibbs Duhem. You can write this way: T delta mu k is RT dln gamma k plus RT dln x k, right? Because the other part, what about, so you have this, right? Dln gamma k, right? You have mu, delta mu is RT ln. So delta mu is nothing but RT ln a k or RT ln gamma k x k. Or here it will be RT ln gamma 1. So you are taking a binary solution. This is gamma 1 x1, and this is equal to this guy. Only this guy, this guy is equal to that, and this guy is equals to RT ln gamma 2 x2. Now you do a chain rule. So d delta mu 1 is RT dln gamma k plus RT dln xk. So now you have x1 RT dln gamma 1 plus dln x1 plus x2 RT, because x1 is there already, right? This is Gibbs Duhem. So x1 times RT times dln gamma 1 plus dln x1 plus x2 times RT plus dln gamma 1, x2 times RT plus dln gamma 1. This has to be dln gamma 2 dln x2, right? Because this is RT ln gamma 2 x2, right? So x2 RT dln gamma 2 dln x2, and there is dln gamma 1 plus dln x1. This is dln gamma 2 plus dln x2 equal to 0. Now x1 dln x1, so RT you can cancel out, RT and RT you can cancel out because it's equal to 0. RT is a constant. Now x1 dln x1 plus x2 dln x2 is nothing but dln x1 is x1 by x1 dx1 plus x2 by x2 dx2, which is dx1 plus dx2, which has to be equal to 0 because x1 plus x2 equal to 1 and dx1 equal to minus dx2, right? Since therefore this is equal to 0. So x1 dln gamma 1 plus x2 dln gamma 2 we can show using Gibbs Duhem to be equal to 0, right? So basically we can tell that if I know gamma 1, I can get gamma 2 again by the Gibbs Duhem integration, right? See, ln gamma 1 I can get. Now ln gamma 1, if I want to do that, x2 equal to 0 again is a pure solvent, right? x2 equal to 0 is the pure solvent or pure component 1, and x2 is the composition, so any composition in the mixture. So we can again use the same Gibbs Duhem integration. Now I'll just come to a very interesting point here, which is called dilute solutions, right? Dilute solutions. So for example, here are these different laws that you can get. Raoult's law. So this is Raoult's law for solvent. Okay, for dilute solutions, if I have a solvent 1, say I have a multi-component system where 1 is solvent, okay, which because the amount, and 2, 3, C, all of these are solutes. Now, if x1 tends to 1, that means the solvent is very, very large compared to 2, 3 and all the other solutes. So the solute concentration is very small. So x1 tends to 1. So then Raoult's law states A1, that's the activity of 1, is equal to x1. That means when x1 tends to 1, it becomes pure solvent. For a pure solvent, the activity of 1 is the same as the, if it becomes a pure solvent 1, the activity is equal to mole fraction, right? That's what Raoult's law tells. Actually, for any component, if that component is large enough, right, compared to the other components, right, for any component, AI equal to Xi is basically Raoult's law, right? So for any component we can write, and if AI equal to Xi, we are basically telling that for the other, so AI equal to Xi is basically an ideal, right? It's an ideal definition. So Raoult's law is basically for ideal solutions. And again, in the limit x1 tends to 1, A1 goes to x1. Now there is some other very interesting law that comes in, which is called, now this is the thing. So when I talk about dilute solutions, Raoult's law is for ideal solution. Raoult's law is more about ideal solutions. It's not really dilute solution. Ideal solution means A k equals to xk, because gamma k equal to 1, right? So for any component, right, we can write. But if you see, even it follows for dilute solutions, because if x1 tends to 1, when 1 is solvent, then basically A1 will become equal to x1. So basically, if you have more solute, for example, if you have more solute, there is a deviation from Raoult's law, but as soon as the amount of solute decreases, it becomes so dilute that the solvent is like pure solvent, then again you get back the Raoult's law. That is correct. But for Henry's law is for solute. So when x2 tends to 0, so this is for solute. So x2 tends to 0 is the dilute solution limit. So this is called x2. x2 is your solute. Say 2 is your solute. 2 is solute. And x2 tends to 0 is called dilute solution limit or dilute solution. When you define dilute solution, we are telling that the concentration of solute tends to 0. Now, in such a case, A2 can be written as gamma 2 0 times x2, or sometimes it is also called KH x2, or this is the Henry's law coefficient, and gamma 2 0 is independent of concentration. Gamma 2 0 is independent of concentration and is called Henry's law constant. Okay, and it depends, however, gamma 2 0 depends on both the solute and the solvent. Okay, so Raoult's law can also be written this way. When you look at this a gas dissolved in vapor, the gas dissolved in a liquid solution or a solid solution, or basically if you have a solvent which is a liquid or a solid, and then you have a gas that is dissolving in this liquid or solid, then we can write that the ratio of partial vapor pressure of each component to its vapor pressure as a pure liquid solid solvent is approximately this. So basically Pi is 0. So basically what we are telling is, this is the vapor pressure of component I when it's a pure solvent or pure solvent. So basically I, pure solvent, then there is a partial vapor pressure, right, which is in there is a vapor pressure of component I, okay, for a pure solvent, which is stated as Pi is 0, right? This vapor pressure, this vapor is in equilibrium with the solvent, right, when I is a pure solvent. So when pure, then again we are using this superscript of 0, and then we are telling now the partial vapor pressure when these components are mixed is equal to, again proportional, equal to mole fraction of component I times the vapor pressure exerted by component the vapor of component I when I is a pure solvent, right? So you have a solvent. If you have a solvent, then there is always a gas phase, right? So if you have a solvent right there, then there is always, so you have solved component I, and this is component I in gas phase, and it is in the liquid phase. Okay, and now in the pure form, the vapor pressure exerted by I in the gaseous state is P0I. Okay, however, when you have a mixture, of different components, then basically you have, again I is there, but then there are other components, and here also I is there in the liquid phase. But what we are telling now, this is Pi, and that is equals to, now what is the relation between Pi and Pi naught? That is related to the mole fraction of component I. That is what Raoult's law states, right? So that is what Raoult's law states. So this is another alternate definition of Raoult's law. So if you look at this, you have, say for example, mixture of two liquids or two solids like AlBl or AsBs, we could have written. So there are two solids A and B, or two liquids A and B, and they are mixed, and you have this here A liquid plus B liquid, and also for A liquid there is a gas, and for B liquid there is a B gas. So basically there is a vapor. So this is A vapor, this is B vapor, and if you look at that, you can use star for pure substance. So if it have been only A, there is no B, then mu A star, that is in the pure state, equals to mu A 0, that is some standard state, plus RTLN PA star. Okay, and the solution of A and B, again mu A equals to mu A 0. See, now this is what we are trying to distinguish. So star is for pure substance, but A 0 is some standard state. Some standard state, where this standard state can be some very small amount of B, or whichever we want to. So mu A 0 is a standard state. Mu A star is that of the pure substance. Okay, so there is the chemical potential of component A when A is completely pure, and this is again related to PA star, which is the vapor pressure of component A, the vapor pressure exerted by the vapor that is in equilibrium with the pure liquid A. Okay, that is the ln ZI RT ln PA star. So now if you have solution of A and B, then it is mu A, and this is PA, which is the partial pressure, okay, partial vapor pressure of component A, okay, when you have a solution of A and B, right? Again, you can write now, but the mu A 0 is standard. Now if you look at that, you can equate mu A 0 in these two equations. Let this be equation 1, let this be equation 2. If I have 1 and 2, now I have mu A 0, which is from 1, it is mu A star minus RTLN PA star, and which is equal to mu A minus RTLN PA. Now in this case, I am considering A plus B solution, and in this case, I am considering pure A. Okay, I am considering pure A. Right here, I am considering pure A. Now, if you see, this is both mu A 0, so I can equate this. So what I get, mu A, now you see mu A 0 is eliminated, and now you get mu A star, which is again the pure form, the chemical potential of A in the pure form, and which is equal to mu A, which is the chemical potential of A in this mixture, plus RTLN PA by PA star. And PA star is that of pure liquid A, okay, the vapor pressure of the vapor phase, which is in equilibrium with the pure liquid A, and this is the partial vapor pressure of component A that is in equilibrium with the liquid solution. Okay, so in that case, you have PA by PA star, and PA by PA star, basically you can write this as mu A star plus RTLN XA, and so PA equals to XA PA star, right? We can write PA by PA star is nothing but XA. Okay, so mu A equals to mu A star plus RTLN XA, and if you look at that, this is PA star, which is for, now this is XA equal to 1, that is pure A, this is pure A, right? So this is pure, and this is pure. So there you have PB star, right? So if you have pure B, you have PB star, you have PA star here, and this is the XA, how it is changing. So as you can see, you have, if you look at just pure A, it starts from 0, and moves to PA star. Again, if you look at PB star, so it's pure B, and this is, so basically pure B means XB equal to 1, and here XB equal to 0. So it starts from here and then goes down and comes here. Now the total pressure is coming along this line because it is XB PB star. So this is basically the line of XB PB star plus XA PA star, or we can also write it as 1 minus XA PB star plus X. So P is equals to that, right? So basically you have a P that is changing, PA or PB that is changing according to this relation. Okay, so this is for an ideal setting. Okay, Now think of this. Why is this Raoult's law? What is the physical meaning? What's the molecular interpretation? Again, every time we look at that, right? So we have this blue colored or blue bordered solvent molecules here, as you can see, and you have these green solutes here, some green solutes, some solute here. Now if you have rate of evaporation, which is basically proportional to the mole fraction of component A. Now, and rate of condensation is proportional to the partial pressure of component A. Now, if you see K prime PA, so if you see at the steady state or at equilibrium, these rates are equal, right? Kxa equals to K prime PA, right? Rate of vaporization. So, solvent can vaporize, solvent can also condense, because there is always, if you have a solvent in the liquid state, it's in the liquid state, it is also there, this is like A in liquid state, then there is also A in the gas state, right, which is A in the gas state, which is in equilibrium, right? So there is a liquid vapor equilibrium, that's what I am considering. So if I consider liquid vapor equilibrium, that means the rate in that equilibrium, rate of vaporization of the solvent from liquid to vapor is equal to rate of condensation of the solvent molecules from vapor phase to the liquid phase. Okay, so Kx equal to K prime PA, or PA equals to K by K prime XA. Now pure liquid or solid, if you think of pure liquid or solid, XA equal to 1. So P star, so basically if it is pure liquid or solid, P star is K by K prime, right? Because if you remember Raoult's law, P equals to PA equals to XA PA star, right? XA PA star. So basically P star equals to K by K prime, thus PA equals to XA into PA star. So solvent and solute, if both obey Raoult's law, then the solution is called ideal. Okay. Henry's law basically does not care about ideality. It is for a real solution, but with a very low concentration of solute, right? Very low concentration of solute. Now in that case, the vapor pressure of the solute, okay, vapor pressure of the solute is PB, right? When XB equals to 0, see PB, okay, this is Henry's law. Now if you see Henry's law very carefully, you can see this line is drawn at XB tends to 0. See, this is the tangent that I have drawn to this curve. This is a real solution, so there is a deviation from Raoult. Raoult's what? That PB equals to XB PB star, right? Or PA equals to, right, PB. So if you have 0 to PB star, 0 to 1, so this is basically XB. The slope is basically PB star, right? So 0 to XB. So the slope here, so PB star is the slope for Raoult's law. But here the slope is, so this is the slope for Henry's law, right? So Henry's law is for a real solution with very low concentration of solute. Now, if you have higher concentration of solute, then there is obviously this deviation, as you can see here from the red line. So this part, this is where I draw the tangent, and that is giving me the Henry's law. And Raoult's law is basically telling me PB, so this is PB, is the partial pressure of P. So basically PB equals to XB, PB equals to PB star, PB equals to PB star, XB, and XB is the x-axis, right? XB is the x-axis, PB is the y-axis, and PB star is the slope, right? PB star is the slope. Other way, Henry's law is for a real solution, but at dilute concentrations of solute. Okay, so basically you can call some solutions which are called ideal dilute solutions. Okay, ideal dilute solutions where solvent obeys Raoult's law while solute obeys Henry's law. Okay, so look at this mixture of acetone and chloroform. Okay, and you have this, so basically chloroform is denoted by C, and acetone is denoted by A, So this is a mixture or a solution at 35 degrees Celsius. At 35 degrees Celsius. Now if I look at that, there is a PC. Okay, that is the partial pressure of component C as a function of composition. Right, you can see the composition of chloroform is increasing from 0 to 1 as a result, and there is also a corresponding increase in the partial pressure of component C from 4.7, 11, 18.9 and all this. And again, as the solute, the concentration of C increases, there is PA that changes from 46.3, then 33, and then it goes to 0 when X equal to 1. Right, so it falls, right, that A falls, right, A is acetone. So acetone initially when X equal to 0, that means it is pure acetone, the vapor pressure was 46.3, pure acetone vapor pressure 46.3, then it became 33.3 when you have 0.2 chloroform or 0.8 acetone, this is 0.6 acetone, this is 0.4 acetone and 0.2 acetone and 0 acetone, then basically the partial pressure goes to 0. Now if you look at this, these are your experimental data points. These are your experimental data points for this is component C. Now component C increases from 0 to 1, right? So this is for component C, right? These are the points for corresponding to component C. And these are the points corresponding to component A, right? This is the point corresponding to component A. So this is for pure A and this is for pure C. Right, so pure C. Now, if you look at that, you can see that the Raoult's law basically tells that the partial pressure of this component, say for example, partial pressure of component C equals XT XC times P star, right? So basically P equals to P star XC. When I tell PC is PC star, so PC star is where PC star is somewhere here, right? So basically Raoult's law basically gives me the yellow lines, right? That's the yellow line. Similarly, I can write, if I look at Raoult's law for component C or component A, I can write P A star XA PA or equal to PA star to 1 minus XC, right? So you can see that there is a minus PA star slope, right? So this has a slope is minus PA star, and PA star is here. PA star is here, right? The slope is minus PA star and PC, so I can also write PC. So these are all Raoult's law. Raoult's law I'm drawing using, that's why I'm using yellow pen, right? Raoult's law. And PC equals to PC star C. Right. So now, but Henry's law, look at Henry's law. Henry's law is drawn at the concentration of the solute, which is negligible, right? So if we look at C, the concentration of solute means A equal to 1 here and A equal to 0 here, right? If I look at XA increases this way. Now if you look at that, when XC is basically very small, that is where you have to draw the tangent, right? That green tangent. So the green tangent basically gives me a partial pressure value of the activity, that's gamma 2 value. So this is basically gamma. So let us look at this line. The green line is basically here or here, say. So this is basically equal to gamma C0, right? So this is the constant and this is basically gamma A0, right? Because when I'm looking at A as the solvent, then basically when A as the solute, the limit of A to, so C is the solvent, A is the solute, then we have to draw the tangent at C equal to 1, right? So at C equal to 1, so this gives me the gamma A0. So this is basically called, these are the constants from Henry's law. So this is something that is often used in liquid solutions, okay, in liquid solutions or solid solutions, and we look at that. But remember, the data points show deviation from ideality. The data points show deviation from ideality. Right? So the data points here are showing. So if you look at this white curve, it is deviated, right? It is either showing it is showing a deviation from ideality. It can be a positive deviation. Here it may be a negative deviation from ideality, right? Here it is showing a negative deviation from ideality. So that's the idea. So partial pressure of oxygen in water, for example, is 21 kPa, and Henry's law constant, say for example, is given by 7.9 10 power 4 kPa kg per mole, and Pb equals to Kb Bb, where Bb is the molality of B, okay, or so basically B here is O2, so B equal to, you can take B equal to O2, then BO2 is PO2 by KO2, where KO2 is already given, Henry's law constant, that is how much of oxygen is dissolving in water. So we can basically see it is 2.9 10 power minus 4 moles per kg. So the concentration of O2 we can see that it is millimoles, 0.29 millimoles per liter. Okay, so basically what I am trying to say is that, say for example, this is one example of dissolution of oxygen in water, and you have very little amount of oxygen, right? Millimoles, 0.29 millimoles of oxygen in water, okay, per liter. And so basically you can apply, right, the Henry's law. But here we are using, so the Henry's law can be written also in terms of molality. So here this is the molality of solute B. Okay, molality means per kg, right? Per kg. So Bb, yeah. So BO2, for example, is these many moles per kg of the solvent, right? Per kg of the solvent. Solvent here is water. Okay, so there is another property which is called collective property or colligative properties, right? These are called colligative properties. Colligative means it does not depend on the nature of the particle, but it only depends on the collection of particles. Colligative comes from this word collection, because of the solvent, because of the solute dissolving the solution, right? Say for example, sodium chloride dissolving in water, you have now 2 moles of, means if 1 mole of water you consider, and you have 1 mole of sodium chloride, you have added to say 1 liter of water. Say let us consider 1 liter of water, and you have added 1 mole of sodium chloride. 1 mole of sodium chloride means 1 mole of Na plus, 1 mole of chloride ions, right? 1 mole of chloride. So 2 moles of Na plus ions and chloride ions, and these are the particles. We do not care about whether it is sodium ions or chloride ions, but we only care about the collection of these particles that are added to water. Okay, and they are dissolving in water. So in that case, what generally happens is, if you look at the phase diagram of water, so this is pure water phase diagram, right, which has, say, at 1 bar pressure, it has a 0 degrees Celsius as the freezing point or the melting point, and 100 degrees Celsius as the boiling point. So we will continue this discussion of colligative properties in the next week, and we will go into how to define quasi-chemical models for real solutions. Okay.